Okay, we're good. So today we'll discuss the concept of adders. Well, I hope it sounds a little bit familiar because we discussed adders before. We discussed the ripple carry adder version before. So today we will take a deeper dive. So in the previous discussion, I chose to bring it forward in the lecture because you had some lab assignments and it will help to just get some exposure to adder, right? And also because of the truth table, it made sense to bring it forward, and it's also a function that has two output. So it's a system that has two output, sum and carry. And we looked at a lecture that specifically dealt with functions with multiple outputs, right? So I feel like it will be an easy example for you to relate to every once in a while that, hey, remember adders that had multiple outputs? There are many other functions that have multiple outputs. That's why I decided to bring it up a little bit forward. But now we are taking the deeper dive into the adder discussion. All right. So let's start. This is a recap of what we have seen before, and I hope you remember it. If not, that's why the recap is there. So an adder basically adds two binary numbers. All right. And when I say binary number, both of them can have multiple digits. So it could be a 4-bit adder that adds two 4-bit numbers, or 8-bit adders, or some, whatever bit adders, for example. So it doesn't matter how many bits of adders you're dealing with. We actually specifically deal with what's called bit slice. So what I mean by that is, imagine you have 1101 and 1001 that you're trying to add together, right? You deal with one bit at a time from every number. So that's called a bit slice. This is a bit slice. This is another bit slice. So you deal with one bit at a time. So the circuits that we are designing, this is for a single bit, not for the entire number, as you can imagine, right? And the interesting part about adders is once you design a bit slice, you could just repeat it for as many times as you need. If it is a 4-bit adder, repeat it 4 times. A 16-bit adder, repeat it 16 times. That's the easiest possible scenario. But there are more involved adder designs where we collectively design the circuits. Instead of designing bit slices separately, we could always design blocks like 4-bit, 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 and so on. And we'll see an example like that in this lecture. All right. So give me 1 second. All right. Okay. So this is the truth table for the adder. We have seen that before. You have 3 inputs, A, B, and C. A and B comes from the 2 numbers you're trying to add. These are the 2 bits of the numbers that you're trying to add. What is CI? That is the carry from the previous stage. Now, imagine you are trying to add 2 numbers, which we just saw. Maybe let's make it simpler. Say 1, 1, and 0, 1. When you add these 2 digits, you get in binary 1, 0, right? So you just leave 0 as sum and provide 1 as carry to the next stage. So notice you are providing a carry to the next stage. For the next stage, you have 3 inputs essentially. You have the 2 bits coming from the 2 numbers, and you have the carry that is coming from the previous stage. Okay? So there are essentially 3 inputs to an adder, and that's called a full adder, which can handle 3 inputs. 2 coming from the numbers, 1 coming from the previous stage add. Can anybody notice something? No matter which 2 numbers you are adding, the first bit slice, I hope you now understand what bit slice is, right? The very first bit slice, the very, let's see, 1, 1, 1, 1. The very first set of numbers that you're adding, does it have any carry input? It always starts from 0 carry. Only after that, there is a possibility of generating a carry. So the first one is special. Keep that in mind. Keep that thought in mind. We'll come back to this. But except for the first bit slice, every other bit slice will require 3 inputs. Even if the carry is 0, you have to account for it, right? Coming from 2 numbers and 1 carry. So that's why you have 3 inputs. And in terms of output, remember, you have to generate the carry to provide to the next stage. So carry is one of the outputs. And also sum is the other output. So you have 2 outputs. And we discussed this manually. There was a separate lecture. I hope you remember this. We added these 3 numbers and saw what happens when you add 0, 1, 1, 1, 1, 1, 1, 0, 1, and so on, right? We discussed this in detail. Okay, so apparently this is the truth table we dealt with, and we converted that into Boolean function, and we got sum equals A XOR B XOR C, which if you break it down, it will be something like this, a longer function. But XOR is more relatable, like 3-input XOR, which is a unique scenario. And carry was AB plus BC plus C. That was easy, functional output eventually. And we also saw how to convert this into a circuit. Notice, if you have A XOR B XOR C as your sum, take an XOR gate. This is the symbol of an XOR gate. You're taking A XOR B and you're doing an XOR with C here. So this is your sum. This is your carry in. Notice you're doing an A XOR B XOR C. Okay. So you're using 2-input XOR gate, 2 of them to do 3-input XOR. That's one example. And also notice you are doing carry out using A, B, and C again, A, B, B, C, and C, A, basically. So notice you are getting A, B here, and this is another AND gate that is giving you the rest of it. There is another way which I didn't show you before. There is another way to represent the carry out. Instead of doing this AB plus BC plus CA, you could also do some algebra, some calculation, and convert it into this format, where you have AB and the rest of it, BC plus CA, could be converted into this format, where you have an XOR output and an AND gate. Am I making sense, folks? So that's what this circuit is implementing. It is not implementing AB plus BC plus CA. That's why you don't see 3 AND gates. You see 2 AND gates and an XOR gate. Are you still with me? Okay. This could be an interesting exercise for you to try out. Try to get this from this. Or if you want to make it easier, do the opposite. Like start with this one and try to get to the other one and see whether you can do it. Basically, just break down everything and do some Boolean calculation, and you arrive at either of them. If you cannot do it, talk to me. All right, I'll show you how to do it. But apparently, you might be wondering, why would we do this? This is not the only way to represent carry in a different format or sum in a different fancy format. Okay, we will see one other example which is very unique in this lecture, and there are many other approaches that people have seen over the years to find out clever ways to make sum and carry work. And there are always reasons. Just it's not like, oh, there is another way to do sum and carry. That cannot be the argument. You have to achieve something by going through that approach. For this particular example, you can reuse some gates. Remember, reusing gates was a big deal for us. So you can reuse some gates. You can reuse at least one XOR gate and so on. That is the biggest selling point. Okay, so without further, by the way, get used to this symbol as well. I know I used a block kind of symbol in the last lecture when we discussed adder, which is fine. For example, I used a symbol like this. This is from one textbook, but this is from another textbook. They all use different symbols. So get used to these symbols. This is an easier to show symbol. For example, you have input A, B, and carry, and then you have 2 outputs, sum and carry out. I'll be using them interchangeably every once in a while so that you're used to both. Okay, now, the view of a ripple carry adder. In some cases, people call it carry ripple adder. So it's basically the same thing. You are rippling, it's as if the carry is rippling through a chain. Okay, that's why the name ripple carry adder or carry ripple adder. What happens here is you add 2 numbers. Give me 1 second. Okay, so you're trying to add A and B, and A has A0, A1, A2, A3, so 4 bits. B has B0, B1, B2, B3, so again 4 bits. You're adding them. You start with a carry. The very first stage will always have a 0 carry, as you can imagine. Okay, so you start with a 0 carry, and then all the other carries will be generated based on the computation that occurs here in this block. And by the way, this FA stands for full adder. And this full adder, if you remember from the last slide, this is the full adder. Okay, so in every block, you have this circuit sitting in there. And that circuit is generating sum and carry. Okay, you provide the carry to the next stage, and to the next stage, and to the next stage, and then eventually you get the final carry. So notice what is being relayed from stages to stages. Is it the sum bits or the carry bits? What is being conveyed from one stage to the other? Carry. That's the name. Carry is being carried essentially. Sum directly goes to the output. It's not given to anybody else. But the carry will, just for a second, think about the significance of that. Your next stage cannot do any computation before it knows what the carry is. Can it? Can it do anything? So it will just sit there for a while until this guy finishes computing sum and carry. And then the second stage can start doing its business. And then the third one, and then the fourth one, and eventually you get the carry. So you see, you cannot do this thing in parallel. If you're dealing with 16 bits, there will be 16 stages per se. So the carry will basically ripple through the chain. That is a problem, and I'll show you the reason why it's a problem. But I hope you can appreciate the fact that this unique architecture will be slower, okay? Because everything else will just wait for the carry to arrive. Okay, and also get used to this direction. In some textbook, they show it from left to right. In some textbook, they show it from right to left. It's all the same, whatever makes sense to you. Okay, now let's move to the next one. So now there is no longer recap, as you see. So these are gonna be new concepts. Please pay attention, all right? Okay, now, what we have discussed so far, whenever you have A and B and carry as input, so there are 3 inputs, that's called a full adder. But did I just show you that there is one special bit slice, which is the very first one that doesn't require a carry input, right? So for that, you could always use just 2 inputs, A and B. Why bother using carry input? You might be wondering, okay, what's the big deal? I'll just put the carry as 0. You know what the big deal is? The big deal is by going from 3 input to 2 input, you could significantly reduce the number of gates and inputs, okay? And let me show you how. So this is the structure that we have just seen before. This is sum, this is carry. And the reason why we chose to express the carry this way is because we are trying to reuse this version. I hope by now you should know that reusing makes sense, right? Okay. So that's why instead of, even though the original carry expression was simple enough, we decided against it. We decided to make it a little bit more complicated to make sure we can share. Okay, now look at what happens when you have just 2 inputs. You just need 2 input XOR, and the carry is nothing but an AND operation. Done. Okay, consider AB, BC, CA. This is the regular carry. AB, B carry in, which is CI, carry in, and A. If carry in is 0, both of these terms will be 0. So all you have left is AB. Don't you think? So, okay. Then you could just represent this sum and carry with two logic gates instead of how many? 5, right? Isn't that a significant change? So if you're wondering, okay, what's the big deal? I'll use a full adder and make the carry 0. Instead of doing so, if you create something called a half adder, this is often mentioned as a half adder, that significantly reduces the area. And that's a big deal. And it is even a bigger deal. You haven't seen that here. It's not part of the syllabus, but I teach it in 433, for example. There is a lecture on multiplier, adders and multiplier. Okay, let's go back to primary school. We don't have to deal with binary, even decimal. How do you multiply? Remember, say if I ask you to multiply 123 with 78, what do you do first? You multiply every digit, right? And then you multiply all the other digits. And then what do you do? After you multiply individual digits, what do you do after that? Add. See, so multiplier has many adders. You probably haven't seen. You need to add every column eventually. So you had many adders in a multiplier, and multipliers require humongous number of adders. And that's when we see that by using half adders selectively, you could significantly reduce the overall area. And that's why half adders exist. Does that make sense, folks? Okay, so I'm getting ahead of myself. So that's the reason why I wanted to have a separate discussion about possibility of using half adder and full adder. So save some area using a half adder on bit slice 0. Notice going through these lectures, we are not just learning and getting grades. We are educating ourselves and familiarizing ourselves with technical terms that engineers use. So bit slice, right? like sounds like a slice of bread, but apparently it's a very interesting thing that engineers, computer engineers always use. Okay, bit slice is essentially a single bit that you're dealing with. And why bit slice 0 is so special? Because it doesn't require any carry. Okay, all right, move to the next one. This is again a recap. We saw that before. Subtractor, remember folks? How do you subtract in a 2's complement format? You basically take, maybe you're trying to get a minus b. You take the 2's complement of b and add it with a. That's how we do it. How do you get 2's complement? You how do you get 2's complement? You take 1's complement of b and then add 1 to it. That's how you get 2's complement. Okay. What is 1's complement? Take a number and basically just invert it. That's what 1's complement is. Are you all good? Okay. Notice here what's going on here. You have b, all the bits of b being fed into inverters. So what you get here is an inverted format of b, don't you think? So essentially, this gives you the 1's complement of b. These are all 1's complement. How can you make it 2's complement? Remember the very first carry that you never needed to use because the carry was always 0. And we were even planning to use a half adder there so that there is no option to even provide any carry. Okay, hold on a second. Instead of doing so, if I use a full adder and make the first carry 1, so that will be like adding 1 to the 1's complement of b, don't you think? And that will convert it to 2's complement of b. And apparently this adder will behave like a subtractor, essentially. So I hope when you see a circuit with the first carry being 1, the first thing that should pop up in your head is, oh, it's a subtractor, essentially. Okay, these type of questions are often trick questions that your potential employers can ask you to see. Anybody can answer, honestly, given enough time. If I give you enough time to think about it. But honestly, in real life, you don't always get enough time to think about stuff. Do you see movies, right? Like all those engineers like trying to fix stuff when things are breaking down here and there, right? So I always wonder, how do they always figure it out, right? They never show that, oh, these guys couldn't figure anything out. The hero died, everything. Never happens. They will always figure things out. Because that's because people only remember the people who could actually solve the problems. They don't remember the people who fail to solve the problems, essentially. Okay, so what I want you to do is practice enough and familiarize yourself enough so that you could be quick about it. I know all of you can do it, but can you do it quickly? That's the question. Okay, so this is also a recap. Now, this is new. This is not a recap. Just to show you that you could reuse the same hardware. Remember, computer engineering is all about, I mean, if possible, reusing components, because the more we reuse, the less area we use up, and that opens up more area for extra features. Okay, extra features. Remember that. So using a simple XOR gate, it is possible to switch between an adder and a subtractor. Here's how. Ready to hear about it, folks? Okay. Imagine you're trying to do b plus a or b minus a. So the only thing that could change is a. It could either be positive or negative. Okay, so let's do that. All right. So take an XOR gate and use a control signal. And the control signal could be either 0 or 1. And okay, forget about everything else. Forget about we are trying to do subtract and write. Just look at the XOR gate. This is an XOR gate. And this is a conventional truth table of an XOR gate. Nothing new here. Absolutely old stuff. Okay. An XOR gate will give you 0 when both inputs match. So if you have 1 and 1, you get 0. 0 and 0, you get 0 again. Okay, that's how the XOR gate works. Okay, now notice one thing. When the control signal is 0, A is basically conveyed to the output as is. So if A is 0, you get 0. If A is 1, you get 1. So your A doesn't change. Apparently, A prime becomes A. You guys all agree with it? Or no? Notice one more thing. It's like going back to the same truth table that we saw before in XOR gate and looking at a new insight. And the other insight is, okay, when the control signal is 1, whatever A you provide, you get the invert of it. You see that, folks? 0, 1 becomes 1, 0. So essentially, when control becomes 1, you have A equals A prime. So by toggling between this control signal, making it 0 and 1, you could either make A inverted or not. Okay? Are you still with me? Yes.
The triple buffer just have inside it XOR gate.
I'm sorry, could you repeat that?
Does it just have an XOR gate inside it? Is that how it?
That's a great question. That's a great question. No, we typically don't do that. All right. There is a reason why we have a separate buffer. The primary reason is we have to generate enough current to drive other gates. Okay. We have to generate enough strength. So they are not always just designed with a single XOR gate. Okay. There are reasons why XOR gates, for example, XOR gate is essentially a Boolean logic gate. It has limited drivability. Okay. And sizing up an XOR gate, I briefly discussed this in the class, but since we didn't discuss the sizing of logic gates in any level of detail, I didn't want to go into too much detail of it. But this is definitely covered in great detail in 433. There are separate lectures. And actually, I have a sneak peek. Let me show you one thing. I'm going to show you here, and I wrote beyond scope. It's not part of the course. Okay. You haven't seen this view of any of the logic gate. This is a view of an adder in terms of circuit. Where do you learn it? In 433, because that takes you through the circuits, internal components of the gates. Right now, you're living at the gate stage, not getting inside the gate. Okay. But when you get inside the gate, then you'll hopefully clearly understand what is the difference between, using an XOR gate to fan out versus a buffer to fan out. Okay. But that's a great question. All right. Let me go back to this point. And do you see that I can just use a control signal to toggle between A and invert of A? And then you could use the same argument, use a carry in and make it 1. Oh, by the way, by inverting A, what do you get? You get 1's complement. Am I going too fast? Okay. By inverting an input, you get 1's complement. And then once you add 1 to the 1's complement, you get 2's complement. And adding 2's complement is basically subtracting. So you could either, so when you add, you make your carry 0 and you make your control signal 0. That means A prime, this A cap is just A. So then you have B plus A essentially. But when you want to subtract, you make your carry 1, you make your control 1. That way your XOR output becomes A prime, which is essentially 1's complement plus 1, which is 2's complement. Okay. Yes.
For the first one, see the XOR.
Yeah, exactly. You can do it. You can do it. Of course. It's a great question. And oftentimes, by the way, reusing depends on the rest of the components, right? Remember, nothing works in like isolation. So an adder will always be part of a bigger circuit. So there are always opportunities to reuse a signal across multiple blocks. So that's why, reusing is always good. Okay, so now we will reconsider the carry logic. And I already gave you a hint, and I hope you remember that. So once you start working on a full adder, it is calculating. You might be wondering, okay, how long it takes to calculate? Just it calculates like a bolt, like a thunderbolt. Duh, you have a sum, you have a carry, done. No, you will appreciate how long it takes. That's why I have this circuit actually, because I keep referring to something that doesn't, show up in front of you. So you may not even get the feel for it. I decided to use this slide from my 433 lecture. Notice one thing. Remember carry in? This is an input. And carry out is basically what you get, right? Output. So essentially, let me change the color here. This is your carry out. Can you see, folks? C0 is your, CO is your carry out. This is the output signal. Where is CI? Can anybody help me find? Carry in. 1, 2, 3, 4, 5, 6. See the distribution of carry in here? They're distributed across different transistors. And the transistors, did I tell you that every transistor has multiple terminals? Gate, drain, source, right? And body. Gate terminals have what? Capacitors. Did I tell you that before? Capacitors. So if you have carry input connected to 6 transistor gates, that means it is driving at least 6 capacitors. Gate capacitors are, concerned, by the way. They take more time to charge up or discharge. So when you are trying to drive, you have a single input, which it's like the single input being routed in 6 direction. You don't have 6 carry in input, by the way. One input connected to multiple gates. So it is simultaneously driving at least 6 capacitors. Could be more, by the way, but at least you can see that in front of your eye. At least 6 capacitors. It is bad enough to drive one capacitor. Just think about driving 6. So it takes a while for the carry in to change the capacitors enough for the circuit to eventually make a decision. Okay, so it's a slower process. Do you appreciate it now or no? Okay, so this is just one stage. So that's why when you provide a carry input, it doesn't automatically lead to a sum and carry. It takes some time, charges up all the capacitors, and there is a delay. And that delay is called the carry delay, T carry. And it takes some time to create the sum as well, because the sum will also depend on the carry input. And you have to let the carry settle. What do I mean by letting it settle? You have to let it use enough time to charge up the capacitors properly. Okay, and that means there is a delay for the sum generation and there is a delay for the carry. Are we all good so far? Okay, notice who is the limiting. Okay, how long will you have to wait? Imagine you are trying to add a 4-bit digit, 4-bit number with another 4-bit number. Okay, so when can you say that my addition operation has completed? When all 4 sum bits are available and the final carry out is available. Do you guys all agree with it? Even though you have the first sum and first carry, it doesn't make any difference because you're still waiting. You cannot basically just consider it's done. So you have to just look at the last stage, not any other intermediate stage, the last stage. So we define the adder delay, which is T adder, based on how long it takes to eventually generate this carry, because that is the slowest signal. You guys all agree with it? Okay. Now let's see, how long will it take to create that? So you have to propagate the carry. So there is 1 carry delay, 2 carry delay, 3 carry delay, and then finally you can create. Are you still with me? Don't give up. So 1 carry, 2 carry, 3 carry. This is carry propagation delay. So in a 4-stage combination, you will be waiting for 3 stages of carry propagation. Does that make sense? So imagine there were n bits. So how many stages of carry propagation would you be waiting for? Please try. Let me take a step back again. Let's follow the journey of the carry input through the chain. This is my carry input that I can control. I gave the carry input. But rest I cannot control, okay? Let's see. It goes through 1 stage, 2 stages, 3 stages, and eventually it arrives at the final stage that I'm concerned about. So in a 4-bit scenario, it goes through 3 stages. Do you guys all agree with it or no? So in an n-bit scenario, how many stages will it go through? N minus 1, 1 less, right? Because we are dealing with the last stage. It's already there. So every stage has T carry in terms of delay for carry. So the total carry delay up to this point is what? N minus 1 T carry. Do you guys all agree with it? That's why this is the delay up to the point where the final stage gets the carry. And now it has to cook the sum and output, right? And how long it takes to generate the sum? You have to wait for that sum to generate. And that sum is just 1 stage. You don't care about what the other stages are doing. You just care about the carry, right? Because meanwhile, all the sum will be generated. By the time the carry appears at your stage, all the sum will be generated anyways. They're never going to be the bottleneck. The final bottleneck is the sum for the last stage, which is just 1 sum delay. So you are looking at n minus 1 carry delay and 1 sum delay to eventually get the final add. Am I making any sense to you so far? Okay, so imagine there is a 32-bit adder. Let's do it just, without any pen or pencil or any slides. Just look at me, all right? Let's try to figure it out verbally. You have 32-bit adder. That means there are 32 stages. Which stage should you be concerned about when you try to calculate the delay of that? The 32nd, the last one. Okay. So how many stages will the carry propagate through to get to the last stage? 31. So imagine every stage has 10 nanosecond delay for carry propagation. Let's take it. Okay. So you have 31 times 10 nanosecond. You guys all with me? And then the last stage will have to do the sum. Imagine the sum delay is like 5 nanosecond. So how many 5 nanosecond will you have to add? Just one, because others will be completed meanwhile by the time your carry propagates. So just one. So you 31 times 10 nanosecond plus 5 nanosecond is your total error delay. All good? Okay. All right. So can anybody tell me what is the bottleneck of this overall array? Is it the sum or is it the carry? I mean, we can clearly see that carry is the culprit here. So you will see many adder architectures, many innovations in adder design just targets the carry optimization. Of course, there are ways to optimize the sum as well, but the most approaches will always target the carry generation, and we'll see that today. I already covered this slide. Actually, I didn't have to cover this, but I wanted to clarify why carry is such a headache for us, because it drives a lot of capacitors. Okay, so now remember one thing, folks. Whatever is carry out for one stage will be the carry in for the next stage. So today's carry out is tomorrow's carry in, basically, right? So this carry out signal is kind of, let me ask you a trick question. I'm trying to, interview you as for example, I'm an Intel hiring manager. I'm trying to hire you, okay, as an intern. I ask you, hey, just look at this circuit. How many capacitors will this carry out drive, at least? In your knowledge, how many capacitors will this carry out drive? Is it driving any capacitor at all? No, it's zero, right? You guys all agree? Is it zero? Is it driving zero capacitors? Or yeah, a little bit, maybe somewhere, like, right? But can you count the number of capacitors? How? No, but see, you're not getting the internship, are you? All right. Yes, go ahead. Thank you. Thank you. You got the internship. Okay. Here's how. Did I tell you that today's carry in is tomorrow's carry out? So these stages, the carry out for this stage is the carry in for the next stage. Look at the carry in. How many capacitors is the carry in driving? 1, 2, I just showed you. 3, 4, 5, 6. So this carry out will basically be the carry in for the next stage. It's the same output node connected to other gates. So essentially your carry out is driving 6 gates at least. So 6 capacitors. Does that make sense? So there is a reason I kept telling you that today's carry in is tomorrow's carry. This stage's carry in is next stage's carry out. Sorry, I just inverted it. This stage's carry out is next stage's carry in. Okay. Are you all good? Okay. I hope I didn't confuse you. Okay. So, all right. What's important is to get a feel for the correlation between different components of the design, rather than just, okay, can you draw this circuit? Sure. You can get an A in your course and everything. After 6 months, nothing will be in your head, right? But if you get a feel for why things are related and why they matter, hopefully this will stay with you. Now, we're going to reconsider the carry logic based on our understanding that carry is the culprit in terms of determining the overall delay or creating a bottleneck for the sum operation to occur. You can read it later on at home. I'm going to cover it anyways using this slide. Okay, please pay attention. This is a very important example. And this is the only example that you will see in this course of a different type of adder. The one you saw is called a ripple carry adder. But this is probably, if not the yours, one of the yours designs possible. But that is what everybody learns because it's so easy and elegant to teach and show and make sense. But others are always going to be more complicated. And this is the first stage that we are going to look at together. And in the very last slide, you'll see other options. And at some point, we'll talk about it in 433 or even beyond. Okay, so we have seen that truth table before. This is the adder truth table. And every time people try to reimagine the adder, they always go back to truth table and try to find a new pattern. Okay. Can we, discuss this in a different approach? Can we not use an XOR gate? Can we use these or that? So they try to always go back to the truth table and find a new way to represent the truth table. All right. So let me show you a renewed understanding here. Okay. I add an extra column. Did you see that? Did you see the animation? This is the truth table that we saw before for sum and carry. Okay, I've added a new column here. And that determines, that indicates the carry status. Okay, let me show you what it means. Please pay attention to when I'm drawing, because after I draw, it will be super messy and it will not make any sense. All right, let's see. Notice for these two rows, maybe you had some carry, but the output doesn't have any carry. So it's as if you have deleted the carry. So somebody is trying to group different rows together based on a comment. So somebody is commenting that, hey, let's consider these two scenarios, delete the carry. Okay, and how about this? Let's take a look at these 4 combinations. Isn't that like, whatever your carry in is, your carry out will be exactly the same? Do you see that? These 4 blocks? Do you see that, folks? So if your carry is 0, your carry output is 0. Your carry in is 1, your carry out is also 1, and so on. Okay. Oh, by the way, why are we grouping them together? Because their combinations are all different. The input A and B are all different, but notice the carry in is essentially the carry out for these 4 combinations. So we are separating out these 4 combinations. So these 4 combinations are special because for them, whatever carry in is you provide, you get the same carry out. Okay, and the other 2 combinations are special because your carry in will be basically deleted. Okay, whatever carry you provide, it's deleted, as if like they're describing it basically. And for the other combination where you have this situation, doesn't matter whether you have a carry or not, you as if you generate a carry by yourself. I mean, that's how they're describing it. Okay, do you see that point here? Do you see that point? So even if your carry was 0, carry in was 0, you generate a carry. If your carry in was 1, you still generate a carry. So as if you don't care what the carry in was, you just generate a carry. So what they're trying to do is trying to get rid of the dependence of carry in altogether and just look at the combination of A and B. Notice, this is a very big comment. Just look at the combination of A and B and decide what to do with carry out. Am I making sense here? Okay, so it will make more sense. I mean, let me take a step back here. Now, let me show you one thing. Okay, let's go back to go to this slide and I'll get back to the previous slide. Okay. Have you seen the sum function before? A XOR B XOR carry in? We've seen that many times, haven't we? Okay, so there is one way to represent that. And by the way, your carry out was A, B plus B carry in plus A carry in. That was the carry function. So apparently, as we saw before, this carry function could also be expressed in this format using A XOR B. So the idea is, let's define A XOR B as a signal called propagate. Why? How does it make sense? Notice. Look at these 4 combinations. Still with me? Okay. Notice, for these 4 combinations, you basically propagate the carry. What that means is your carry in is basically copied to carry out. So they're trying to correlate this observation to a mathematical representation. Okay, so I'll show you what it means. So this is they define this section of the function as the propagate signal, P equals A XOR B. And once you do so, your carry out can be represented as, let me show you. This thing can be represented as propagate. So this is PI, propagate signal. CI, PI. And how about the next one? AB. Remember, your carry out was AB plus BC plus CA, but BC plus CA could be represented as CI, A XOR B, and you are converting A XOR B to propagate. So essentially, you are left with AB. And AB is basically, let me show you, is this portion, generate. Okay, so we define generate as AB. Just define it in a way that it kind of describes the observation in your truth table. So again, this is a stretch kind of. So people somehow try to relate to the observation in a mathematical way. And what it comes down to is, if I didn't give you this insight about the observation at all, just forget that I ever talked about it. Say, if you don't care about it at all, you could just mathematically rearrange this using some intermediate function. Define AB equals G. Don't keep in mind that G stands for generate, okay? Just G. And A XOR B as P. We are not going to look at delete here because that's a different kind of error that people use to incorporate the delete signal. But I just put it there. Some people define a different function, A prime, B prime as delete, D, okay? But that's not part of the design we will cover in this course, okay? So essentially, you could reimagine your sum and carry function as this: P XOR C and G plus PC. It's kind of like representing the same function using different variables. Okay, now all I'm trying to do is show you how the guy who invented it thought about it. What were they trying to do? Essentially, they're trying to somehow physically represent this observation into a mathematical format. So they came up with this, terms called generate, propagate. That's all. Okay, so that's why instead of using any other variable, they use G to represent AB because it relates to generate. The other variable, YP, why not D? Why not X, Y, whatever, right? They try to correlate this to propagation. That carry will be propagated. That's why P. Okay. So now, but if you don't care about all that, just imagine you rearrange these two functions in a way that you get to intermediate expression. Are you all good so far? There is a very big step that I have taken already. Honestly, nothing changed in the sum part. You know why? Because propagate is essentially A XOR B. And you still have C in here. So sum doesn't change at all. It's essentially A XOR B XOR C in. I didn't change the sum, did I? But something changed here. Can anybody see what changed here? Yes. Yes. So essentially, the carry out, notice, you will see the power of this pretty soon, is G plus PC. G is not a function of carry. Only one of the terms. Only one thing is a function. No. Okay, please help me understand. What was P? Quickly, it's written here, A XOR B. Is there any C in the propagate signal? No. Is there any C in the generate signal? No. You have singled out the carry input in just one variable, CI. Okay, I'll show you the power of it in the next slide. In the next slide, if we have the time. I hope we will have the time to show you. It doesn't make sense as of now, but in the next slide, I hope it will make sense. Let's see. It is a lot of calculation, but I'm going to do it myself using an empty slide to help you navigate. Okay, let's consider you have two stages. This is carry 0. This is sum 0. This is carry 1. This is A1, sorry, A0, B0. Are you with me? This is the first bit, and then the second bit will be A1, B1, and your sum will be sum 1, and then it will be propagated to, carry 2, something like that. Okay, so let's calculate carry 1. According to the last example, remember, carry is, so let me show you. Let me just put it there. What is propagate signal? A XOR B. So when I say propagate 0, it should be A0 XOR B0. When I say propagate 1, it should be A1 XOR B1, like every bit, right? Okay, how about generate? What is generate 0? A0, B0. What is generate 1? A1, B1. So every bit has a generate signal, has a propagate signal, okay? So now your carry, if you remember properly, as we just derived, was, we saw it in the previous slide, is generate plus propagate plus carry. So generate plus propagate, which is generate plus propagate plus carry is 0. Can I say that? Any problem so far? Okay, so this is an expression. Now, let's take a look. You'll see the power after we calculate C2. What is C2, folks? C2 will be G2 plus P2 plus C1. Why C1? Because the carry input of this stage is basically carry 1. Don't you think? What is the carry input of this stage? C1. Am I making sense here? No? Remember, this is essentially carry in, not necessarily carry 0, right? Carry in. What is the carry in for the next stage, second stage? The carry out of the first stage, which is C1. So when you calculate C2, this guy will be C1. Does that make sense? Okay, let me quickly finish the next sentence, and then if necessary, I will repeat it. Don't worry, okay? You don't have to take it for the face value, but I want to show you where I'm going with it eventually. So let's keep going. Can I convert this C1 from this equation that we saw before? Can I put C1 here? Can I put it? So then G2 plus P2 times G1 plus P1 C0. This is the first stage carry, C0. Can I do it? And then if you calculate it further, G2 plus P2 G1 plus P2 P1 C0. So you can express C2 in terms of C0. Does that make sense? You see where I'm going with it now? Okay, if I go to the third stage, I know it's getting messy. I'm completely aware of that. Don't worry. We'll revisit it again. I'm just going to show you the end of it. And then we'll go back and redo it again so that it makes sense to all of us. So when I try to calculate C3, I could go through some similar calculation and apparently express C3 with respect to C0. Okay, so that's what this slide is doing. Notice, C I plus 1, I plus 2, I plus 3, I plus 4 is essentially every stage of the carry. And you could do this same calculation and apparently link it back to CI, which is the very first carry input, which is in my example, C0. Does that make sense? After you go through this calculation, every carry could be linked to the very first one. So you don't have to calculate the intermediate carries. You just deal with the first ever carry. Does that make any sense at all? Okay, so we just have 1 minute. I cannot fully repeat that again. Don't worry. Have this idea in mind. I will start with the same concept of carry look ahead, essentially. This is called the carry look ahead approach in the next class, and we'll hopefully begin here and finish up the lecture, all right? If possible, please read what up to this point, read the slide and make sure that you have the questions in mind. Thank you.